us briefly review what we have done with the theory of Riemann integration as of now. Let us also see what we have learned along with what are the difficulties of the methods that we have learned. Note that our permanent goal is to determine whether a bounded function on a closed interval AB is integrable or not, and if it turns out to be integrable, then to compute the value of the integral. So what are the approaches that we have seen or employed up till now? So the first approach is, by definition, we have to compute the UPFs, LPFs, take supremums, infimums, etc. Now there is an obvious difficulty of calculating the quantities UPF and LPF. Namely, you have to look at several subintervals and then compute the absolute maxima or absolute minima of the functions in those subintervals, which are rarely very easy. Next, we have seen a corollary of Riemann condition. So what was the corollary? It said that a bounded function f, so as we had previously said that we will always assume that our functions are bounded real valued function on a closed interval AB, like here. So it said that f is integrable if and only if there exists a sequence of partitions Pn of the interval such that Upn minus Lpn goes to 0 as n tends to infinity. Moreover, it said that if such a thing occurred, then the common limit of UPNF and LPNF would be exactly equal to the integral of f in the interval AB. But the difficulty is, how do we go about choosing such a sequence of interval which will give us this limiting condition? Next, one would always guess that, okay, we have FTC, so we can easily compute the antiderivative of the function that we are given with and use the second part of FTC to compute the integral. Well, it might sound very easy, but in practice it is not very easy to compute antiderivatives. And moreover, it might so happen that an antiderivative of a function does not exist. But in that case, does it mean that we cannot compute the integral, or does it mean that we cannot even estimate the integral of f in the interval AB? So this difficulties give rise or motivate to an idea called Riemann sums. So here we would like to approximate an integral of a function over a closed and bounded interval. So let us see what do we do with it. So as always, we are given a function that is called f from the closed interval AB to R, which is a bounded real valued function. And suppose that we are given a partition. So this is f and a partition P. So again, as we have seen, x0, x1, xn of the closed interval AB. Now, instead of computing the maxima and minima of f over the subintervals xi minus 1 xi, but we can easily compute the value of f at one point, a point that is that we have been free to choose inside our interval. So what do I mean? So this is our closed interval AB. This is our partition. This is x1, x2, etc., xn minus 1. So suppose that here lies this closed interval, subinterval xi minus 1 xi. So here let us pick a random point from each of the interval. Now instead of computing maxima and minima, it is easier to compute the values of the function at the point that we have chosen. So let us write down. So choose T1, T2, Tn in AB such that Ti belongs to the closed interval xi minus 1 xi for I equal to 1 to n. Now we are going to investigate the following sum. So let me call it SPF and define it as summation I equal to 1 to n f of ti xi minus xi minus 1. We are going to investigate this sum, and this sum is called the Riemann sum for f corresponding to the partition P. Now we want to compare SPF, LPF and UPF. So we first want to compare these three quantities. Now we know that for each I, f of ti is less than or equal to big MIF, and it is also bigger than or equal to small MIF. Now mimicking one of our previous calculations, we can easily see that, so this holds for all I equal to 1 to n. So mimicking our previous computations, so let us try to see what happens. So what I have done is that I have multiplied the whole inequality by xi minus 1. Note that that is of course a positive term which maintains the inequality, and since the inequality holds for all the values of I, we can sum them up, and the sum will also preserve the inequality. Now what is the guy in the middle? This is nothing but SPF. What is the guy in the left hand side? This is nothing but LPF. And what is the person sitting in the rightmost side? This is nothing but UPF by definition. So let me call this inequality 1. But this is a very nice inequality. We can see that if I was allowed to choose a random point from each interval, then the value, the Riemann sum that we have taken, would always lie between UPF and LPF. So let us see what is its relationship with the Riemann integral of f over the closed interval AB. Now let me introduce a few terms, or just one term. So I would like to write it in a different color. The mesh of a partition P is given by the following quantity. So I would denote this by mu of P. So now we have the length of the interval. So x1 minus x0, x2 minus x1. So I take the lengths of all the subintervals that I have. This is a finite set, and of course I could take maximum of this set, and I will call it mesh of the partition P. So this is the mesh. Now what has this mesh got to do with Riemann integral? So here is a theorem that I will just state without proof. So what does it say? So let f be integrable on the closed interval ab, and let epsilon greater than 0 be given. In this case, then there exists a delta greater than 0. These deltas, as you have seen in calculus, always depend on the epsilon value that you have chosen or it was given to you. So depending on epsilon, there exists a delta greater than 0 such that UPF minus LPF is less than epsilon whenever mesh of P is less than delta. So this is a very common way of explaining things in calculus, as you may have understood from this course and the course before. But here we are going to omit this proof. But what is more important is a corollary, which is rather sequential in flavor, and it will be really useful in understanding Riemann sums and their relationships with the Riemann integral of the function. Okay, so what is the corollary? Let f be integrable on the closed and bounded interval ab. Suppose that there exists a sequence of partitions, Pn such that, so these partitions are partitions of the closed interval ab, and I have not written it, such that mu of Pn goes to 0. Okay, so mu of Pn goes to 0 as n goes to infinity. Then UPNF minus LPNF goes to 0. This is our first claim of the corollary. Now comes the Riemann sum. Let SPNF be a Riemann sum corresponding to Pn and F corresponding to not the sequence Pn but Pn, the partition, and the function F. Then SPNF goes to integral ab fx dx. So formally written, integral ab fx dx is equal to limit n tending to infinity SPNF. So I'll come back to this notation just after proving this very beautiful corollary. So I want to prove this very slowly, but the reason of going through the proof of this corollary is that one of the reasons is that it is very important. Next, the proof is really beautiful, and it really uses most of the things that you have seen up to now in calculus 1 and calculus 2. but the proof is very short also. So let's see. So let epsilon be greater than 0. So let epsilon greater than 0 be given. So by the previous theorem, so why the previous theorem is applied in this case? Because f is integrable. So see, what we had done is that if f was integrable, then this theorem holds that for any given epsilon there exists a delta such that UPF minus LPF is less than epsilon whenever mu p is less than delta. So since f is integrable on AB, so let me make it a small b. By the previous theorem, there exists delta greater than 0, of course depending on the epsilon, such that whenever mu p is less than delta, we have UPF minus LPF, this is less than epsilon. Okay, so let me call this observation star. Okay, so now what do we know? So we know that mu pn is goes to infinity, goes to 0 as n goes to infinity. So we have mu pn goes to 0 as n goes to infinity. Now apply the definition. So by definition, I will use this delta here. So for the given delta, there exists n0 a natural number such that mu pn is less than delta whenever n is bigger than or equal to n0. Okay, so now we have seen when this condition is always satisfied, mu p less than delta. Okay, so but we have seen that mu pn less than delta implies that UPF minus LPF less than epsilon. So here UPNF minus LPNF is less than epsilon. Now let me try to tell you what we have done. So we had started with an arbitrary value of epsilon which is greater than 0. We have found after several steps that there exists an n0 such that whenever n is bigger than or equal to n0, then UPNF minus LPNF is less than epsilon. So let me write down this again, whenever n is bigger than or equal to n0. But what does it mean? So you can apply the definition of convergence of sequences, and this will just tell us that UPNF minus LPNF converges to 0 as n goes to infinity. And in turn, what does it give us? It gives us that limit n tends to infinity UPNF and limit n tends to infinity LPNF. These two limits are equal. Okay, so we have now proved the first part of the corollary, that UPNF minus LPNF goes to 0. So of course this goes to 0 as n goes to infinity. Okay, so now we have to prove that condition which is related to Riemann's sum. So we have to show that in such a case, if such a case is satisfied, then SPNF goes to integral fx dx as n tends to infinity. Okay, so let us try to show that. Now by equation 1 that we had at the beginning of this introduction to Riemann sum, we have seen that LPNF, whatever be the partition, I do not care, but I will always get this inequality. This we have proved rigorously. So I do not know, maybe I should call it 1 prime. So this is nothing difficult, but we also know by what we have seen before that LPNF is less than or equal to LF. Now what is LF? So LF is nothing but equal to integral ABF fx dx. So this happens since f is integrable. Now integral fx dx turns out to be equal to uf, again because of the same reason, since f is integrable, and we know that uf is less than or equal to upnf. So now let me call this 2, and let me also write down what we have found. So summarizing what we see is this two inequalities. So LPNF less than or equal to SPNF less than or equal to UPNF. So this was our equation 1 prime, and we also have LPNF less than or equal to integral AB fx dx less than or equal to UPNF. This was our equation 2. I make a claim here. My claim is that modulus of SPNF minus integral of AB fx dx is less than or equal to UPNF minus LPNF. So let me try to prove this claim. So proof of claim. So what do we need to show? So this is a small aside. So what does it mean if I want to show that mod x is less than or equal to y? It simply means that x lies between minus y to y. So here we have to show similar things, but it is not very tough to do that. So first we make use of the following inequality which we get from our equation, our inequality 1 prime. So SPNF is less than UPNF, and integral AB fx dx is bigger than or equal to LPNF. So I do not know, let me call it something 3, call it 4. So if I do 3 minus 4, what do we get? SPNF minus integral AB fx dx. This is less than or equal to UPNF minus LPNF. Similarly, we have to show that this quantity is bigger than or equal to LPNF minus UPNF. I could have left this as a very simple exercise, but since I am doing this completely, so let me try to do it as well. So here we get another kind of equations. So SPNF is bigger than or equal to LPNF. So this we get from our inequality 1 prime, and we also know that integral AB fx dx, this is less than or equal to UPNF. So let me call it 5, let me call it 6, and if we again do 5 minus 6, we could see that SPNF minus integral AB fx dx, this is less than or equal to LPNF minus UPNF. So consequently, by this aside, we can see that the inequality that we were looking for holds true. So this proves our claim in particular. SPNF minus integral AB fx dx, modulus of this is less than or equal to UPNF minus LPNF. Now we know that the right hand side, so this is so this completes the proof of our claim, but here we know that this right hand side goes to 0, and of course, since we have taken modulus here, this quantity is non-negative. So SPNF minus integral f from AB is less than or equal to UPNF minus LPNF, and this is bigger than or equal to 0, right? But so this claim holds for all the values of n, and we can easily see, or not easily see, but we are given that this goes to 0 as n goes to infinity. And by sandwich theorem, we can now easily prove that SPNF minus integral ABF goes to 0 as n tends to infinity. But this term is a constant, so this implies that SPNF goes to integral of f on the interval AB dx. So this completes the proof of our corollary. So now let us try to summarize what we have done. As we have seen that if f is integrable, so if f is integrable, the only thing on the sequence of partition that is important to us is the mesh of the integral. So what we have seen is that if f is integrable and Pn a sequence of partitions, such that mesh of Pn goes to 0, then SPNF goes to the integral ABFX dx as n goes to infinity. So writing in terms of limit, we have limit n tending to infinity. So what was our definition? I equal to 1 to n f of ti xi minus 1 is equal to integral AB fx dx. Okay, a few remarks are in order. So you may ask me that what if I instead of choosing a given ti, I had chosen another element from the interval, but then after taking the limit here, we have seen that it will not matter, because we have not really made use of any particular property of ti. And in fact, you can choose your Ti to be you can choose your Ti freely, and this will work because we have now proved the corollary using the theorem that we have not proved. And this set is called tag set. Okay, so you can choose any tag set and it will work. In general, we will mostly choose Pn to be the Pn that we have seen in our previous lectures to be the partition of AB into n equal subintervals. So we have seen this before, Pn's before. So what is Pn? So in particular, Pn is given by a plus, so a plus b minus a by n, a plus 2 times b minus a by n, etc., and it finishes at b. So this has divided this into n subintervals. And what are the length of the subintervals? Length of the subintervals are denoted by delta x, which is given by the quantity b minus a by n. Finally, let me try to give you an idea of why is the symbol of integration. So the symbol of integration was actually introduced by Leibniz. So this mathematician called Leibniz, who first introduced this notation of integration, and from the properties that we have just proved of integration in terms of Riemann sums, what does it look like? So a b fx dx is equal to limit as n tends to infinity. As we have seen in this very particular case, this is also equivalent to saying that the mesh of Pn goes to 0 of S Pnf. And what is that? So this is limit n tending to infinity summation I equal to 1 to n f of ti and delta x. So what was delta x? Delta x was xi minus 1, length of the subintervals, which was equal to p minus a by n. And here, what is the length of the interval? As we have just said, that it is b minus a by n, which is constant, which does not depend on the values of I. So we could write it as limit n tends to infinity b minus a by n summation I equal to 1 to n f of ti. So we may imagine that the whole thing here boils down to is replaced by integral, the sign of the integral. So we will see examples of how these things work in our next video. For the time being, bye.